In my talk, I want to develop the theme fitness and survival of OR. It was introduced first by Robert Fields and John Ranyards in the 1990s. Within this general theme, I'm going to address the current hot topic of artificial intelligence. So, what's going to happen to our chosen profession in the light of AI? Can we envisage a time when a robotic device such as this says, "Hello, I'm your OR consultant"? Of course, saying anything about the future is inherently tricky, but actually, writers of science fiction and futurology have rather a good track record. From Arthur C. Clarke, who anticipated communications satellites, to George Orwell, who imagined the social consequences. One of the oldest such imaginings was the film The Automatic Motorist. It's about a metal robot that could drive a car. It was made in black and white in 1911, over 100 years ago. Brave New World, 1984, and Stand on Zanzibar are all novels about future dystopias. John Brunner's Stand on Zanzibar, written in 1969, paints a scenario as follows. The year is 2010. Under the leadership of President Obama, I kid you not, President Obama, the United States is plagued by random acts of violence, including school shootings and terrorist attacks. Cars are powered by rechargeable electric fuel cells. Detroit is an abandoned wasteland, and so on. I think you'll agree it sounds pretty eerily similar to America today. Remember, it was written 50 years ago. Now, in this lecture, I won't be addressing the wider social impact, which is undoubtedly one of the big issues of the day. Instead, I'll be addressing a much narrower question. Will the rise of powerful artificial intelligence be the best thing that ever happened to the OR profession, or the worst? And given that immensely powerful AI is definitely coming towards us, what should we do? Actually, today we are inundated with books providing insights into this new world, not in the distant future, but now. In this lecture, I'm going to bring together two premises. My method of attack will be to draw on sociology, economics, and logic to look at the relationship between these two premises. So what is the potential impact on professional practice in general, not just OR? Richard and Daniel Suskins have already addressed this question. They've come to the view that there will need to be retraining and redeployment, but in the long run, there will be a decline in the need for traditional professionals. This gives rise to a whole bunch of questions for OR. Does this apply to OR? Are we special and different? If so, when and how quickly? First, I propose to look at computerization in professional practice as I have experienced it. I started my professional life as an engineer indentured to Sir Gilbert Roberts, the world's most famous bridge designer at that time. One of the projects he worked on as a young man was the Sydney Harbour Bridge. But he made his reputation with the Forth Road Bridge and the first Severn Bridge. And they were in the 60s. One of his incidentally, he's not only Sir Gilbert Roberts, he's a fellow of the Royal Society and winner of their gold medal. He was a big name in those days. One of his great achievements was to find elegant and efficient ways of dealing what has come to be known as flutter. The Tacoma Bridge collapsed in 1940, shortly after opening. The effect was unexpected, as dramatic as you can see. Unexpected because the wind actually wasn't very powerful and it was really steady. But it caught hold of the bridge in such a way that no one had ever anticipated, and you can go on YouTube and see the video of what happened. It's a very dramatic failure. Now, when you design a bridge, the first drawing is known as the general arrangement. Here is the general arrangement of the Severn Bridge. From that one drawing, 10,000 drawings result. So from one drawing, you get this enormous amount of engineering effort to finally provide the necessary requirement for a bridge. Now, I was given the task of, in effect, fitting the Severn Bridge over the rather bigger Bosphorus Gap. This is the drawing I did. Now, I presume you can't see very much of it, but you might just be able to see at the top a bit of it. It suffered from sitting in damp cellars and on bookshelves with the light coming through. And it's a long time ago. Well, you can hardly see it, but it's a general arrangement, I assure you. Such designs at this stage are just an exploration, a sort of imagining. They're usually part of a feasibility study, but they very seldom result in anything actually being built. But this did. And if I can find it, here it is. The bridge was opened in 1973. A beautiful sight, I hope you will agree. It's what they call nowadays the first Bosphorus Bridge. In those days, it was just the Bosphorus Bridge. The Turks were so pleased that they, and I've lost my, anyway, they put it on their 1,000 lira note, and you can see it here. Now, the surprising thing, I did this initial design after only a couple of months in the job. And the reason I could do it, because it was a very, very simple thing to do. And the key was structural analysis. I've mastered technology, as you can see. Right, so the key to this is structural analysis. If you go from left to right of the diagram, on the left there was the standard assumptions that have to be made about the properties of steel. At the top are the standard engineering samples, which you make simplifications to make the analysis possible. And on the right you have the things that you've got to achieve with this bridge or any other structural device. And in this case, for instance, the bridge had to be far enough above the water to allow the Black Sea Naval Fleet to pass underneath. They would get a little bit upset if they weren't able to do that. Now, I did the calculation in 1967 with pencil and paper. At about that time, the late 1960s, computers were starting to be used. The programs were written in-house and ran on mainframes. So my experience as an engineer was and still is fundamental to my way of thinking. And so when I studied at Warwick for an MSc in OR, I could immediately relate to the way that mathematical models were used in OR to inform decisions. From the left, we have the assumed constraints. It's all familiar stuff to you. On the above, we have the analytical assumptions, for instance, linearity, and then on the right, we have the goals to be achieved. As you'll see, it's very, very similar. My lecturer at Warwick, by the way, was none other than Robert Dyson, a past president of the OR Society. Once again, I learnt to do the LP calculations by hand. When I started to work at the NCB's Operational Research Executive, I found that they had developed some in-house mainframe programs. So both engineering and OR technologies have moved from pencil and paper to mainframe computers, thus making life easier for the professional engineers and scientists and speeding up the whole process. By the time I'd left the NCB, we used packages running on PCs rather than mainframes. So I'd had a good introduction to the use of computers to solve mathematical problems that could be represented in mathematics and which can help decision makers think about a particular problem in the real world. The point is that both engineering and in OR, you no longer had to do certain things by hand. The central function analysis had been computerized. You could say that the programs were an early example of artificial intelligence. The human was no longer doing it, but the computer was. The programs were able to replicate analysis that would have otherwise been done by humans. They did it quickly, without error, and without the need for coffee breaks. That's roughly where computerization of OR stood when I decided to join academia in 1991. The title I chose for my inaugural lecture at Warwick was, and this is going to be no surprise to you at all, Building Concepts to Reality. Building Bridges, Concepts to Reality. You can read it, I can't here. Clearly I still had bridges on my mind, but the concept I wanted to focus on was binary representation. That was the miracle. It seemed to me something of a miracle that Shakespeare's writing, Beethoven's music, and Picasso's paintings could all be reproduced using noughts and ones. In my lecture, I talked about the implications of this miracle for business. But I also thought it might be a good idea, now I was going to be an academic, and this is what I thought academics sort of do, to declare my research agenda. So I declared my research agenda, and it was this. The first item on the agenda was to capture the process of OR as I had experienced it. Towards that end, I wrote and published a number of case studies, some of the consulting projects which I had undertaken. On the basis of these case studies, I once again did what academics do. I started theorizing. Out of the process of reflecting on the cases and theorizing, I developed a way of looking at things which I call the transformation competence perspective. This perspective simply focuses on bringing together, on the one hand, deciding what it is that's to be achieved by an OR intervention. This is the transformation, the task to be achieved, and so on. And on the other hand, the skills and abilities, the competencies that can be brought to bear to the task in hand. A very simple idea, more or less a statement of the bleeding obvious. The tricky bit is that the two elements, transformation and competence, have to be co-determined and agreed with the client. The next step was to develop a schema of OR competencies, that is to say, the habits and skills that OR practitioners develop and trade on. Here is my attempt to do this. The framework has three legs. On the left we have conducting analysis, and I've been talking about some of that just now. In the centre we have designing and managing the process of intervention, more or less project management. On the right we have appreciating context, that is the workings of the client organisation and the social, political and commercial conditions. Relevant to all this are the all-important craft skills in the top left-hand corner. And I'll be coming back to this diagram later. But it's important to recognise that the client competencies are also relevant. Furthermore, we can take advantage of the expertise of other members of the client organisation, perhaps other stakeholders, and sometimes an outside expert or two. But in the first instance, I want to concentrate on the client. It is the all-important relationship between the consultant and client that is all-important. These are my two archetypical, well, I better be careful. They're not too archetypical, are they? It's a bit sort of gender stereotyped, if I can put it that way. Anyway, I comfort myself that one of them might be transgender, and maybe that overcomes the problem. Fundamentally, the relationship is a personal one. Both client and consultant will have their own ideas about the sort of relationship they want to have. The knowledge and expertise of the two people will be asymmetric. Each party comes with a different set of values, access to networks, and different abilities and power to get things done. It is this asymmetry that provides the value of collaboration. And it is the trust that builds between the two parties as they interact and explore these asymmetries that provides the confidence to proceed. The interaction between client and consultant is, of course, a social activity within a social context. One way that sociologists look at social interactions is to utilise actor network theory. This is how it looks. We can start with a very simple representation of the client-consultant relationship. At the centre of the network are our two good friends, the OR practitioner, that is the P, and their client, That's the C. Both practitioner and client also have relationships with actors within the organisations of which they're a part, their inner context, and with people outside their organisation, the outer context. Altogether, these actors and their relationships form an actor network, a very simple conceptualisation. Of course, it's more complex than that, more actors and more network relationships. Clients may well have other contacts in your consulting firm. You and your colleagues might have contacts with other members of the client's organisations. These contacts could be work-related, or they could be more personal, old university colleagues, family, neighbours, or members of organisations, such as professional bodies, or indeed membership of the same church or Masonic lodge. Network theory goes a bit further. It suggests that material things can also be actors. Now that takes a bit of getting your head around. Material things don't sound like actors, but that's how they conceptualize it. A mainframe or mini computer is shown here. At times during the flow of action, human actors have to follow the routines and instructions coded into the computer system. You have to feed data into the computer and wait for the computer to process your input. The computer then allows you to move on to the next screen. It's the word allows you that indicates that the computer is in control of the action. The computers therefore need to be depicted as part of the network. In the OR concerting world of the 1990s, the network evolved. You have the internet linking multiple PCs on the desks of the actors. Today we have the cloud. The cloud acts as a store, a source of information, a repository of software, and provides access to search engines and social media. The level of communication and interaction has grown rapidly. I've also added the yellow pentagon with an H in it, which stands for the habits of OR practitioners, another active element in the network. Habits sometimes take over, driving what we do. We are in this sense a slave of our habits. We lose control and we are uncertain about a factual statement. We search for empirical evidence. Sorry, I read that badly. When we are uncertain about a factual statement, we search for empirical evidence. When it's a matter of opinion or belief, we seek out a variety of opinions. When we are considering an argument, our own or that of others, we puzzle over the inherent logic. These are three important OR habits: the empirical, the interpretive, and the critical. And in practice, we worry away at how these three interact and to inform decisions. It's determined not to help me here. Okay. Now, when we come to analyze this and when we try and apply this to AI in OR, we immediately hit a problem. And the problem precedes any other sort of analysis, which I would like to do, which is an economic analysis, because economic analysis seems to be a way of cutting through some of the complexity that I've introduced. So when you read the books about the third wave, the seventh sense, the fourth industrial revolution, and so on, how can we make any sense of this? In effect, the authors are choosing different events to characterize major historical change. There seems to be agreement that the agricultural and industrial revolutions were historically significant. Then there is some debate about the relevant importance during the last century of oil, the combustion engine, and network electricity. But in this century, it's apparent that all are agreed that a digital revolution is underway, with AI at its forefront. But we immediately hit a problem here, because the term artificial intelligence seems to be a collection of multiple applications, and it's difficult to find a crucial test to tell us what is AI and what is not. Furthermore, such things as optical character recognition, which were originally hailed as AI successes, have now just become an accepted computer technique. Meanwhile, we keep getting announcements that this or the other problem is being or will be solved by AI. The fact that old things that were considered AI have kind of dropped off and new things added on has led one observer to suggest that AI should be defined as whatever has not been done yet. So we have a problem. We need to think about how, wow, that suddenly worked. How OR has been itself seeing AI. Well, we generally take it as being a relatively recent phenomenon, despite my comment that it goes actually way back. And is understood as the latest manifestation of computerization. Each phase shown here allows more of the human work to be carried out by computers better and more efficiently. To see how quickly AI in OR might proceed, I'm going to try and cut through all this complex and dynamic reality exposed by actor network theory and look at some simplicities. Engineers always seek simplicity. To do this, we can take advantage of the insights of economics, specifically the relatively straightforward economics of technology penetration. I think the bit that I missed out, because I couldn't find it here, was actually saying that when you've got the social science bit, when you've got your actor network and you've got all these different actors interacting, the key insight is that if you change one bit of that network, all the other bits have to change to get it back into some sort of equilibrium. So it's dynamic. And so if you're going to hit it somewhere, anywhere in there, with some new AI, some new way of doing it, which is going to change things, all the other aspects change, particularly with your clients who are being hit by this, having to change things radically, and at the same time deal with Brexit, the environment, and whatever. So it's a very difficult, dynamic thing to understand how that whole actor network works. So I want to turn now to economics, which I usually get a groan, at least when you mention it. But the relatively straightforward economics of technology penetration. I first used this economic theory when I worked in the National Coal Board. They were interested in the penetration of new mining techniques. I found this market penetration model fitted the historical facts very well. It fitted lots of other things very well. But the theory says that the take-up of new technology follows a bell shape, the blue curve. The take-up of a new technology goes from various stages, from innovators to finally laggards. The green curve shows the cumulative effect on market penetration. This takes the form of a logistics curve. In the 1950s, the economic reasons behind the logistics curve have been established empirically by a very detailed analysis of the take-up of hybrid corn in the American Corn Belt. The study analysed the economic forces driving the substitution. In today's term, this is the same as the penetration of genetically modified crops. But the results back then were very clear. Changes start where advantage is greatest, and that seems fairly obvious. But the thing I want to draw your attention to is the third finding, and that's a crucial one. This means that the speed of penetration is faster the greater the economic advantage of the new over the old. And it is slower the greater the investment required in the new facilities to enable the change. This result has since been confirmed in many, many fields. And the result gives us a handle on trying to estimate the rate of penetration of a new technology. So where is the application of AI on the logistics curve? What do we know about the economic drivers? Well, there are three well-established laws, so-called laws. The first is Moore's law, and I think most of you will be familiar with Moore's law. Transistors per square inch is just a proxy for speed, power, and reducing costs. As the power of computers has been doubling every couple of years or so. This is a plot of this happening, and it's over 50 years since this law was first formulated. People state it now, but don't remember just how long ago this whole thing started. I think we all know that a smartphone today has more power and storage on capacity than anything they used to have. In fact, when I saw anything more powerful, the most powerful mainframes when I started out were not as powerful as my iPhone. I find it difficult to envisage this doubling every couple of years or every year or so. So I'm going to try and help that by getting you to visualize the impact of exponential growth. So try this thought experiment. Imagine a large football stadium which is conveniently waterproof for what I'm about to say next. And it's full of people right up to the top. And a drop of water falls on the pitch. Then a minute later, another drop falls on the pitch. And then a minute later, 4 drops fall on the pitch. Then a minute later, 8 drops fall on the pitch. 49 minutes later, the people at the top drown. Now, it's kind of graphic, but that's not really the interesting thing. Because the interesting thing is that after 45 minutes, it's only 17% full. People sitting at the top will look down and they'll just see that the pitch is covered with water. Not a problem. No need to panic. 4 minutes later, they're drowned. And they won't have anticipated they needed to do anything. Well, that seems to me as a sort of metaphor for the wave of the fact that computing costs are going to go down, and that's going to be the driving force making things happening. The first part of that equation, I said, if the economic advantage is great enough, things will happen. And so that is what's driving it. The second law, Reed's law, just says that as more and more people engage with the internet, they will find more and more ways of using the ability to communicate and coordinate. So this is all multiplying, and that's also driving things. The third law is a rather interesting one, because it says that the hype of new technology outruns the reality. This is a source of much confusion. Initially, 50 years ago, there was huge enthusiasm and research dollars for AI. As long as 50 years, they called it AI, and that's what they were trying to do 50 years ago. Followed by disillusion and non-renewal of research contracts, and all went quiet for a time. But stimulated by faster and cheaper computers, enthusiasm has recently regenerated, and now AI is the big thing. This type of pattern, the manifestation of Amara's law, can be represented graphically like this. The diagram shows early hype, followed by a period when reality sets in and interest fades. Many new technologies then drop out and you don't hear of them again. Others, the winners, start to be recognized as practical when real applications are reported. Confidence mounts, and these technologies take off up the logistics curve. It is the pattern of perceptions that tends to dominate reality much of the time, and it's only towards the end that reality and perceptions start coming together. And this is all referred to as the market curve. And this is some of the technologies plotted on the market curve a few years ago. The internet and the mobile technologies are growing rapidly, were growing rapidly, followed by the cloud. which was at an earlier stage. If we turn to OR, where are we on the market curve? How rapid is the penetration likely to be? To address this question takes me to the third topic on my research agenda, namely, what is the fundamental service that OR provides? In my view, OR develops arguments for its clients. That's its fundamental nature. It develops arguments for its clients. And not any old arguments, but arguments that are rational. So in general terms, what are the requirements of a rational argument developed during an OR inventory? What exactly is entailed? Well, I suggest that we can start from the position that our arguments need to be creative, logical, fact-based, warranted, and persuasive. In all of these aspects, logicians, ancient and modern, have had something to say, rather too much to say. Let us return, perhaps I should reword that, rather a lot to say. Let us return to my basic depiction of a simple OR model. The yellow box in the middle represents a computer algorithm designed to solve mathematically defined problems. In terms of logic, or mathematics if you prefer, these algorithms can be represented and solved using deductive logic. But we have a problem with the constraints, the things around the outside, the constraints, the analytical assumptions, and the goals. These introduce simplifications, approximations, and estimates. They are all sources of uncertainty. However, we can still represent all these uncertainties and estimations in the language of philosophical logic. The type of logic that addresses these issues is called modal logic. So we have the deductive logic for the central thing, and for the things around the outside we can use modal logic. It provides the means of extending the computerization of the logical deductive core. Thus, deductive and modal logic together can be used to represent all aspects of OR modeling. There is currently an explosion of interdisciplinary development of modal logic involving philosophers, mathematicians, computer scientists, and AI developers. This is crucial. We now have an increasingly powerful way of representing our OR reasoning in logic, and we have available ever more powerful computers to calculate the consequences and draw conclusions. And furthermore, we can logically defend or warrant the arguments derived from the modelling. Thus, if we return to the OR offer, here it can be seen that the logical and fact-based and the warranted aspects, the ones in the centre, can be represented with the help of deductive and modal logic. That leaves the creative and persuasive aspects. On these, as indicated in the diagram, philosophy has something to say, but creativity, persuasion are not particularly logical activities and seem to call for the human touch. So, seen from a technical and logical point of view, AI can model our core reasoning, but of course other things come into the picture. So let's have a look again at our competencies to see which might be taken care of by AI. This is the diagram of the competencies that I showed you earlier. If we pick out those that have already been largely or to a great extent computerized, those are the ones shown there, and there will be increasing efforts to extend computer coverage. Then it all becomes rather more difficult. We start coming up against activities that humans are rather good at and the computers find rather difficult. We can conclude that there are some aspects of OR that practitioners should be able to hang on to for some time. These we can call the residuals. Our survival lies in doing the residuals well. They are our competencies that computers will struggle to match. I should have put that through so you could see it. These are the ones that computers will struggle to match. The residuals involve judgment, communication, creativity, and developing an appreciation of context. As we increasingly focus on these aspects, the center of gravity of our competence moves from analysis to the residuals. We can thus distinguish between those competencies which are reasonably easy to represent in terms of deductive and modal logic, and those which are much more difficult to describe and model, the more human characteristics. In the AI community, there is agreement that there are two radically different types of AI. One they call artificial narrow intelligence, or weak AI, and the other is artificial general intelligence, or strong AI. However, the idea of strong AI came under attack as soon as it was posited. The strong AI position was articulated by Herbert Simon in 1965. He contended that all aspects of human intelligence could be replicated by computers. But within the same year, Hubert Dreyfus responded in a Randward paper arguing that the essence of our experience is the human sense, based on our personal goals and all our unconscious intuitions, attitudes, and knowledge. Dreyfus argued that the state of being an expert is when our intuitions have developed to the point where we forget the rules and simply size up the situation and react. This expertise is, he argued, something computers and robots cannot develop in the foreseeable future. Now, it's rather tempting to argue, therefore, we're okay, sort of thing, because the computers will never be able to do it. But there is a problem with that, in that I agree with what Dreyfus had to say, but for us, I think it's the right answer to the wrong question. Because the question isn't whether, for us, whether a robot or AI can actually replicate everything and probably do it better than humans. The question for us is, can something be developed which is good enough to do the functions that we do? So it's this concept of good enough. And I refer to these as type A and type B. Type A is the sort of things that we can do relatively straightforward because it's on the core activities, and type B, which is not strong AI, but a good enough AI for OR. Now, we're now hearing about successful applications of type A. This trend can only gather pace. We're getting papers in our journals, etc., about applications of AI. We can be fairly confident these types of applications will race up the adoption curve. As for type B, the research and development effort in other disciplines is immense. Yet the result is that robotic devices can perform impressive tricks, but are far from exhibiting anything like the width and flexibility of human behavior required for strong AI. So this strong enough may well be sufficient, but the timescales of future development and implementation are extremely difficult to estimate. On the one hand, you have to overcome the huge problems of developing and implementation. And I think a lot of the commentators are right about this, have absolutely no idea how difficult it is to get large computer systems up and running consistently, which are not falling over, which are have all the interfaces that work okay. And I don't think people have, you might have much more powerful computers, but they haven't really got the time it takes to actually bring about these changes. So it becomes extremely difficult. But you have to say against that argument, is the fact that some very powerful and very funded work is going on in the military, governmental and private institutions. Much more than is visible. There's a race going on for who can produce the most powerful AI, which translates into military power, if you like, is one of the issues there. So there'll be a lot of new technology coming out. But I have to do a sort of best guess. As I've said before, that Type A OR AI has been going for some time, but not altogether successfully, and hasn't penetrated very far. Then I think it will still take a good long time for that to continue to penetrate, and who knows how long it will take before it does all the sorts of things that it could do. But the Type B hasn't really yet started, or it might have started a bit in some places. I don't know about it, but it's not publicly known that that's started. So that could take some time. Really, these figures are starting now, and then it's really going to take quite a lot of time, despite the fact that the technology is going to be there, but the actual implementing it and making it all work, making all these things interface, seems to me quite a long way off. It's barely started. We can get some idea of how susceptible jobs are to computerization. Researchers at the Oxford Martins School at Oxford University have tried to distinguish between those jobs that are relatively easy to replace by AI and those which are not. In 2013, they published a paper which examined the impact of future technology by job categories in the USA. The paper contained this summary of their findings. Jobs difficult to replace are on the left, and jobs easy to replace are on the right. This is the source of the oft-quoted conclusion that about 50% of jobs are under threat from computerization. I think you're reading that all the time now. Any article on it seems to quote that. The paper suggests that these two, interestingly enough, occupational categories are among the least susceptible to computerization. Clearly OR, however you like to define it, belongs somewhere in these hard to displace categories. And this seems to reinforce the conclusion that we have already reached the point where OR is in a good place from the point of view of survival, and there are the OR is in a good place from the point of view of survival. There are also many surveys to identify the skills that would be in great demand. We can get some more reinforcement to this in the future. One such survey is timed to provide a discussion point at Davos in Switzerland, whenever that occurs. Good OR practitioners surely develop the skills numbered 1 to 5. I think you would agree with that, yeah? And they will develop that in the course of their education and practice. But I'd also hope that experienced leaders develop 6 and 7. That's kind of more difficult, but I hope we do. But if we go back to the clients, they also have difficult to displace jobs from those two I picked out there. The managers. And they will be aspiring to achieve exactly the same skills. We should therefore have plenty in common with our clients, but also differences in the depth of understanding of some aspects, hence the asymmetries. At the end of the day, the key client-consultant relationship is based on the building of trust, the feeling of joint enterprise, and the expectation that their individual attributes can complement one another. It seems likely that so long as managers are humans, they will seek help from humans. So I think we're locked in together in that respect. but it will be in a very rapidly changing world. So I think there's an area there that we can defend. So what should we do? Here's a to-do list for practitioners. I've already emphasised the necessity of keeping close to the clients. The fourth bullet point about residuals is also crucial. Creativity, if I remind you, flexibility, the understanding of people, the building of relationships, all these are difficult to replicate in computer code. Our survival depends on these residuals. They find us the means to stand, they give us the means to stand our ground. As to the last bullet point on the chart, we have to both support and take advantage of the communities of OR practice facilitated by the OR Society. It is clear that at a time of rapid change, the OR Society will be an important actor at the centre of OR networks. It will have its own dynamic in which we are all participants. The outcome will affect the way potential clients see us and the way we see ourselves. As for academics, in my view, academics need to deploy their well-honed skills to anticipate and engage in the new reality in any way that they can. They need to help practitioners adapt and change. The message is, if OR is to survive, everyone, practitioners, the OR Society and academics, need to get involved now. It's not too early, and it could soon be too late. The computer scientists will take over. We are all actors in this very dynamic actor network, where everything and everyone is going to be mangled. Remember the stadium. We are competent, we're in demand, we are fit, we feel safe. But if we don't do something now, it will suddenly swamp us and OR will be gone. It's a worrying prospect, but it's also one full of exciting challenges and opportunities. And who knows, it might turn out to be all right on the night. We can help it make it so. As to my own contribution, my next step is to buy a personal robot. The CCTV can provide visual evidence of who put what in which cupboard or drawer. And the last bullet point will contribute to a harmonious household, solving the did-didn't arguments, in particular with my wife, Elizabeth. This talk was conceived when looking at this view from our home in Plymouth. The bridge was built in 1859 by the great Isambard Kingdom Brunel at the height of the Industrial Revolution. For me, it's a metaphor harnessing the great advances of technology of the day. It seems like an apt place to finish. Thank you.